On the next few slides, we're going to be talking about a new term, and that new term is called the span. And the span is nothing more than all possible linear combinations of a set of vectors. So the notation for that is span. The braces that you see here represent a set, right? So it's a set of vectors, v1 to vp, and span of that set simply means that we're taking a linear combination of the vectors in the set, and then we want all such possibilities. So from our previous example, we had the vector b equal to 0, 1, and we showed that it could be written as a linear combination of the vectors v1, which is 2, 3, and v2, which is 1, 2. Since we found that b can be written as a linear combination of these two vectors, we would say that b is an element of the span of v1 and v2. All that means is that b can be written as a linear combination of the vectors v1 and v2, which is written in this way. So let's look at the following example. In this example, we have two vectors, a1 and a2, and we want to know whether or not b, which is given by here, is an element of the span of these two vectors. Another way to ask this question is to say, is b a linear combination of the vectors a1 and a2? So to write that as a vector equation, we write it in the following way. And then, of course, the goal is to determine whether or not the linear system is consistent. So is the linear system consistent? If it is consistent, then we know that b can indeed be written as a linear combination of a1 and a2, which in turn tells us that b is an element of the span of a1 and a2. The augmented matrix for the linear system is given here, and if we then put this into row echelon form, we get the following result. 1, 5, 3 is the first row, 0, -3, 14 is the second row, and 0, 0, -92 is the third row. So you see in this case we have an inconsistent linear system, and we know that it is inconsistent because the last row of the augmented matrix is a pivot column. Hence, we would say that b cannot be written as a linear combination of a1 and a2. And we can therefore conclude that b is not an element of the span of the set of vectors a1 and a2. In this example, the question is phrased slightly differently from the previous example, and that is, it says that we have two vectors, v1 and v2, and it says find the span of v1 and v2. So let's talk about what it means when it says find the span of two vectors. So if we were to write that in language, it means find all vectors b that can be written as a linear combination of the vectors v1 and v2. So the way we might approach this is to just choose an arbitrary vector. So let's choose arbitrary b, And let's say that B is any vector in R2. By R2, we simply mean vectors that have two real elements. So the vector looks like B1, B2, where B1 and B2 are simply real numbers. So we'll say they're an element of the real numbers. So the augmented matrix that represents that vector equation or that linear system looks like the following. So V1 is the first column, V2 is the second column, and then the constant column are just the arbitrary values B1 and B2. And so our goal here is to determine which values of B1 and B2 will give us a consistent linear system. So it will give a consistent system. All right, so again, we need to know what values here work. So to answer this question, of course, we need to put this into row echelon form and then determine whether or not, or for what values of B1 and B2 we're going to get a consistent system. So again, we have the augmented matrix for this linear system where B is written as a linear combination of the vectors B1 and B2, and B is any arbitrary vector in R2. So here's our linear system, and what we want to do is take this linear system and put it into row echelon form. So let's do the steps together. So the first goal is to find the first pivot, which is the 1, and we want to take the next element, which is this 2, and make it a 0. So to do that, we're going to create a row equivalent matrix where we're going to take row 2 and replace it with minus 2 row 1 plus row 2. All right, so in this example, the first row does not change, so I'm just going to rewrite it. And now let's look at what happens to the elements in the second row. And I'm actually going to move this bracket over a little bit because I know that the constant term is going to be a little bit longer than what I have there. All right, so let's go ahead and perform the operation. So we have minus 2 times 1 plus 2, which is going to give us the 0. Then we have minus 2 times 3 plus 5, which gives us negative 1. And for the next element, we have minus 2 times B1 plus B2, which gives us our last element in the constant column. So as you can see here, we now have this matrix in row echelon form. So next we want to ask ourselves, under what circumstances does this linear system have a solution? When is it consistent? Well, notice that we have a pivot in the first column and a pivot in the second column, but the last column of this matrix is not a pivot column. Hence, we know that it is consistent. And the important thing to note is that it's consistent for every value of B1 and B2. In other words, the values B1 and B2 that we see up here can be any value. So what does that mean? It means that these two vectors in linear combination will give us any vector in R2. So these vectors will give any, and we can even say every vector in R2. So a shorthand way of writing that is to say that the span of the vectors v1 and v2 equals R2. All that means is that if I take a linear combination of the vectors v1 and v2, I can get any vector I want in R2, and in fact, I can get every vector I want in R2. In this next question, we have vectors v1 and v2. So v1 is 1, 2, and v2 is 2, 4. And again, we want to find the span of v1 and v2. So we've chosen an arbitrary vector, b, in R2, and we've set up the augmented matrix for the linear system. Now you've noticed that I've already done the work and put this into row echelon for you. And one thing that we have to note here is that we have a pivot here. The next pivot is here. So for this system to be consistent, it implies that this term must be 0. Given that, we have to solve the following. Minus 2b1 plus b2 equal to 0. If we solve this, we find that b2 is twice b1. So now let's look at b. b is the vector b1, b2. But notice that we can write b2 in terms of b1. If we do that, we replace b2 in our vector with 2b1. Now both of these terms have a b1 in common, so I'm going to take a b1 out. And so we see that the solution is that the vector b that represents the span of the vectors v1 and v2 is any vector that is a constant multiple of the vector 1, 2. So let's think for a moment geometrically about why we obtained the solution that we just got. So here is vector v1 in the plane. If we draw v2, notice that v2, which is 2, 4, is just twice the vector v1. So here's the vector v2. Notice that for b, we found that it was a multiple, because b1 is just any real number, of the vector 1, 2. Well, if I take a linear combination of two vectors that are lying on top of each other, what I'm going to end up getting is simply another vector that is a multiple of the vector 1, 2. So they'll all lie on the same line.